Hello, in this video we're going to look at the moment of inertia of a sphere, a solid uniform sphere. Now, you may have watched an earlier video I did on a shell, a uniform shell, so a hollowed out sphere. And in that video I went all the way back more or less the basics on working out moment of inertia, and we did a double integral. But I did point out that you can add up um, individual sort of smaller moments of inertia if you can break up a more complicated object into simpler objects, and you can take all of the simpler moments of inertia and add them up, and that will give you the moment of inertia of the composite more complicated object. And that's the approach that I'm going to take in this video, just so you can see the two approaches. In the shell we went back to basics. Here we're going to use previous findings. So what exactly am I meaning by that, just to make it a bit clearer? If we've got this solid sphere, we can divide this sphere into a collection of solid disks. So if we think of all of these disks just stacked up on each other, going from top to bottom, then if we add up the moment of inertia for each one of those disks and integrate those, then we'll get the moment of inertia of the whole solid sphere. So this was the sort of part we sidestepped in the shell discussion, and it was one of the integrals that we did when we went back to basics. We said, okay, in this case we had a whole load of rings stacked up, but rather than adding up all of the moments of inertia of all of those rings together, we did two integrals, one which worked out the ring and then one which integrated all of those. So here I'm just going to do that little bit of a shortcut. So yeah, we do know that the moment of inertia of a disk, a solid uniform disk, is a half mr squared. We worked that out in a previous video. It's quite easy to show. It's only a two-dimensional shape. I suppose in some ways it's three-dimensional. It's got a little bit of pretend thickness in it, but when you get down to actually integrating things, it is really just a surface. You're going to that limit where you're stacking together here disks that the thickness are going down to the limit of zero when you're adding them together. So these are two-dimensional moments of inertia, which are a lot easier to work out. So this three-dimensional solid sphere, we're just going to add up all of these moments of inertia. So yeah, we've got a rotational axis which is going through the center, because this moment of inertia, remember, a moment of inertia always depends on where the axis of rotation is, because that determines the mass distribution. So this finding that we've got here was for an axis going through the center of this disk, and here we've got the axis going through the center of the sphere. So that's all good. So we got that. So we can now say that for each disk, we've got a little bit of the total moment of inertia of the sphere. So we've got a di, and that's the half r squared, and we got a dm, a little bit of mass that we're assigning or working out of each one of these disks. Now we're going to have to unpick all of this in order to turn it into something that we can integrate. So our dm, our little bit of mass, is going to be the total mass of the disk multiplied by the fraction of the volume that we've taken up with this disk. So we've got half r squared, we got the mass, we got to then multiply that by the little bit of volume that we've got, divided by the volume of the whole sphere, which is 4/3 pi r cubed. So here I've already put in the usual stuff, that the mass of the whole sphere is capital M and its radius is capital R. So what is this volume? What is this little v we've got here? Right, now this is where we're going to add in our constant that we're going to be, not constant, variable that we're going to be integrating over. So let's take this as x. So let's have some value x that we're measuring from the center of the sphere up to there. So we've got x, center of the disk, sorry, from the center of the sphere to the center of the disk is our distance x. But we got a little bit of thickness, and this little bit of thickness is going to be dx. That's the thing which is going to go down to our limit that we're going to integrate over, and it allows us to work out the volume, because this volume here is now going to be, we know that the radius of this disk is little r, because we've already used that here. So the volume, the little bit of volume filled up by this disk, is going to be pi r squared dx. And we put all of this in together, we've now got something that we can integrate. So di is going to be equal to, God, there's a lot going on here, isn't there? We've got a half, we've got r to the power 4, we've got an m, the pi's are cancelling, we've got this, which is going to become a 3/4 because we're dividing by the 4/3, so that's now going to become 3/8 as our fraction. And we've got an r cubed, capital R cubed at the bottom here. Yeah, I think that's all of the bits, isn't it? Yep, so we've got our r's, our m's, yes, all of that has gone through. Right, so this is now our thing that we've got to try and integrate. Oh, I left out the dx, the most important thing when I was trying to put the integral back in. Yeah, we need the dx there. So we can integrate this over dx, but we've got this r kicking around. This is the thing which is the variable here. Yeah, we've got a fraction, we've got m and r, capital R, which are constants. But this r, this lowercase r, varies with x. It's a function with x. As we're changing the value of x, r, r is really small here, and it goes all the way out to capital R there. So r is a function of x, and we need to pull out that x so we can integrate over it. And we do that by using Pythagoras. We've got this triangle here, x up to the disk, r is the radius of the disk, and capital R is the radius of the sphere. So little r squared is equal to capital R squared minus x squared. We want to use this in our integral. So putting all that in, we can be able to say that I, because we're going to be integrating the left-hand side, we've got 3m over 8r cubed as the constant on the outside of the integral. And this r to the power 4 is going to be capital R squared minus x squared, all squared, multiplied by dx. And now we have to decide what limits we're going to put on. So we could be saying, okay, well, if we're moving from top to bottom, well, we're going from r down to, we've got r and minus r as the limits here. We also know with a symmetry all of this, so we could put that on. We could say we've got minus r at the bottom here, we've got r at the top. We also know we're going to get exactly the same for the top half as the bottom half, so we could just put a 0. We could do 0 to r on there and then multiply everything by 2, because we're just going to be doing it twice. So I'm going to stick with that, and then we only have to integrate for half the sphere, and this will get rid of, it will make our definite integral easier to calculate what it is. So putting that 2 to get rid of this 8 on the denominator over here, we've now got 3/4 m over r cubed, integral from 0 to r. Let's expand this out. So we've got r to the power 4 minus 2r squared x squared plus x to the power 4 dx. This is easy enough to integrate. Right, we remember that all these capital R's are constants, and we're just integrating for x. So 3/4 m over r cubed, and then we've got r to the power 4 times x minus 2r squared. Then we're going to have x cubed all over 3, and then we're going to have plus x to the power of 5 divided by 5, and that's going from 0 to r. So this is where the 0 lower limit is useful, because we've got x everywhere. We can just ignore that. We can stick these r's in, and then we just got to work out what the fractions are. So what have we got? We got the 3/4 m over r cubed multiplied by, so we've got r to the power of 5 minus 2/3 of r to the power of 5 plus 1/5 of r to the power of 5. So we've got all the, take this, factorize out this r to the power of 5, which will cancel 3 of them with the r cubed. So just put in the final answer over here. We've got 3/4 of m r squared, and then we've got 1 plus a fifth minus 2/3. So 1 and a fifth minus 2/3. So what is that going to be? We'll get this all over 15. So we've got 18 over 15 minus 10 over 15. So that's 8 over 15. The 8 will turn into a 2 when we divide by the 4. So we've got a 2 at the top. And then the 3 and the 15 will turn into a fifth. So 2/5 of mr squared. So yeah, that's the alternative approach. And we could have done something very similar to this. You might even want to go back to working out moment of inertia of the uniform shell, the hollow sphere, doing exactly the same sort of approach, but using the moment of inertia of a ring rather than a disc. You might even want to do this one again using the approach that we used in the shell, where you're not using the already worked out disc answer, and you're going back to having first principles where you're working out little bits of volume. But I mean, it's not exactly critical to do that. I mean, so it's a nice exercise in calculus and working these things out. But providing you can see that both of these ways are perfectly valid, and certainly that you can add up individual moments of inertia of simple objects to get a more complicated moment of inertia of a more complicated composite solid. So yeah, that's a nice one. I think this is probably the last one I'm going to do on moments of inertia. It's given you quite a flavour now. We've had one-dimensional, two-dimensional, three-dimensional objects. A lot of them you just go around, you look them up. It's like when you're doing calculus and things, you don't always go back to doing everything from first principles. You can look up known results for calculus and working out, particularly for integrals. And it's the same with these. If you want to know a moment of inertia, you just look it up. Don't work it out every time. But it's nice to know where they all come from, in the same way as going back to first principles in integration is very useful. You don't want to lose complete sight of where all of this has come from and just be a blinking robot on it. So it's good knowledge to have.